Welcome to my talk called What the F is a Monad. So, before I start, I would like to tell you why I want to be doing this talk. So, I'm a Java developer. I've been using Java since Java 1.5, and up until Java 1.8, I really thought that something was missing, especially when I was looking at other code, for instance, snippet from C Sharp, and they already had Lambda at the time, and it felt really powerful. And I was really happy when Java 8 came out and started playing with lambdas and starting rewriting my code using streams and optional. And as I was reading more about the new features, I came upon the word monad, and I read an article about monad, and this is how I felt. The article was describing a lot of different monads, state monad and future monad and optional monad, and I really could not understand, what the F was a monad. What are these things have in common? So I started um, getting more into function programming, and I started learning Scala and Haskell, and eventually I got to learning category theory, which is an underlying mathematical abstraction that powers functional programming. And this is how I felt. I understood a little bit more what monad was, and there was a bunch of complicated terms, and I still, could not really understand what it was. And then suddenly, one day, boom, I had an epiphany. And suddenly, monad was really clear, and it was so simple. And now I'm like this. The guy getting upset, angry in a good way, in a positive way, I hope, that why a lot of people are worried and scared of what monad, actually, it's something so simple. So before I continue, I also want to give you a disclaimer. This famous mathematician said one does not talk about monad without mathematical rigor. And I really want to disagree with him, with Boromir, because I think a lot of people are scared away from learning what monad is, because they think it's so super complicated. And the reason is for that is because, yes, it is a mathematical object, so it has some serious definition behind it. But I think we can grasp what a monad is, like 95% of the core of what a monad is, without going into the mathematical details. And this is what I want to be doing today. So this was why I'm doing this talk, but why should you care about the talk as a Java programmer? Well, I think functional programming is the new black. I think it's the new hot stuff. Everyone is talking about it. Look at languages like Scala, C Sharp, Clojure, Haskell, JavaScript, pardon me, and Java 8. And Java community is lagging behind. I mean, C Sharp introduced lambdas in 2007, and in Java we had lambdas in 2014. 7 years, it's a long time. Imagine how technology evolves in 7 years. I think there is little knowledge of the theoretical foundations. When I talk with my Java developers, I attend, London Java community groups and that sort of things. Hardly anyone knows what monads are. If you go to a Scala meetup, everyone knows what monads are. Things like functor, applicative monad. And I think that Java is heading more towards functional programming, and I hope it is. And if it is, then I think we should all be prepared and understand the basic principles. So there are a lot of really good talk about how to apply functional programming principles in Java. I'm going to give you two: a pragmatist guide to functional geekery by Michał and a G after F patterns by Mario. But this is not really what I want to be doing today. What I want to be doing is to give you some insight in the theory. I want to simplify the theory so you remember it and you think you can learn it as well. I want to interest you so you want to know more about it. And hopefully I'll help you understand future readings about monads. So before we start, we need to establish some common principles, some common language that we'll be using to have a journey. We're going to have a journey, and in the end, we're going to understand what monads are. So the first principle is called function type. So this is borrowed from Haskell. So if we have an object f, column A, arrow B, it means I have an object f, which is a function from the type A to the type B. So A and B can be any type. They could be integer, they could be string, they could be your own data structures, any. And basically, a type is like a set of values. So here, the type A is the set of circles, and the type B is the set of squares. And my function f will have to map each element of A into an element of B. So if we look at some examples, we could have a parseInt function that takes an int and returns a string. In Java, we would write it the other way around. We would say parseInt takes an int, returns a string. Now, currying is something that we're not really familiar in Java because we are familiar with the uncurried form. So in the uncurried form, a function can have as many arguments as it wants. So for instance, here I have a function f that takes one a, one b, and returns a c. So in Java, we could write the function f that returns a c. I could take my a and my b. I could do some computation with both, and I just return the c. And in the end, if I want to get a c, I will just say f a b, and I'm getting a c. Now, in the curried form, the rule is that you will only, a function can have at most one argument. So how do we handle functions with multiple arguments? Well, the trick is that you keep returning functions. So here, my function, I will write a, b, c. So I would read this as a function that takes an a, that returns a new function that takes a b, eventually returns a c. But really, how I should read it is a function of two arguments. And how it works, well, if I had to do it in Java, it's a bit annoying. Java is not really good for that. But I will have to change the return type to, instead of returning a C, I will have to return a function from B to C, and I just text an A. Then I do some stuff with just my A. Then I return a lambda that gives me access to a B. I do some stuff with my B, and then I return a C. And if I want to apply my function, I'm calling f of A, and then I'm calling, this is a function, then I'm calling B. The interesting thing is that there is a mathematical theorem that proves the exact equivalence of both approaches. So why would we look at curried form? Well, in the curried form, it gives the compiler and also you a bit more freedom, and it allows laziness. So languages like Haskell are heavily based on laziness. So for instance, I could first apply A, and then I could wait, and then I could then apply B, and maybe this gives me more freedom into when I consume my arguments. If you think about an if block, when it takes an A and a B, let's say, or A, B, C, for the condition, the true value and the false value, well, you might not even execute the B value. So actually this code is kind of lazy, and we can do the sort of things better with currying. I think function composition is something that is quite intuitive. So if I have two functions, a function f from A to B, a function g from B to C, well, I can artificially create a new function that will directly go from A to C by first applying f and then applying g. This function is called g after f. So the round operator in the middle is pronounced after. So first I call f, then I call g after f. So if we look at the notations, the types, f goes from A to B, g from B to C, and g after f goes from A to C, and it looks like it doesn't go through B. The interesting thing is that this round after operator is a function in Haskell in itself. It's a higher order function. So it's a function that takes one function from A to B, a second function from B to C. Now we know this is a curried form, and then it returns a new function from A to C. So now that we have some notations, a common knowledge, a common vocabulary, the first thing I want to talk about is pure functional programming. And this is to help us to give some context of where monads fit. So pure functional programming, I like to think it as a philosophy. It's a way of life about writing code. So what does it mean? Well, it means that the programs we write are composed of pure functions. Function, basically, it means that there is no side effect. And I'm going to explain to you what the side effects are. That basically means the function can be memoized. It always returns the same value with the same argument. So if you had a function, let's say from int to int, you could run your function for every possible int. You could store that into a file, and this will be your pure function. And it's strictly equivalent to either call your function or maybe just do a lookup in your cache. So what side effects? Well, you can modify a variable, modify data structure, setting a field, throwing an exception, doing any sort of I/O or drawing on screen. So all of this useful stuff, you can't do it. So of course there are some ways around that, and we're gonna get to that. So it also means that the declarative style is favored over the imperative style. So in the declarative style, the program basically specifies what you want, and in an imperative style, you specify how you want it. So actually here we can already see the intuition is that we should be doing less work because we just tell the language what we want and not how to do it. Yeah, these examples were taken from this book, which I will reference at the end. This was a picture I took on my way to work, talking about exceptions, and you see this is pretty embarrassing. So obviously you will see here that it says .NET. So of course this would never happen in Java, but still I think we should be careful. So interesting thing about exceptions is that exceptions can be seen as partial functions. If I have a function from A to B, and actually some input of A throw an exception, it means that my function is partial. It's only defined for certain elements of A, and some elements, at least one element of A, is not defined. And we can also see that the partial function is a lie. And why is it a lie? Is because if you look at the type signature of a function, it's its contract. And if you look and there's a function that says, give me an A, I'm going to give you a B. Well, oh, actually, no, certain A's, I will throw an exception. Please open the documentation about a function. And it means the function is not from A to B, it's from some A. And that's a problem because it means that the function is not so if the function was part of a library, the person using the library will have to dig into the code and check what sort of input on my set A are not valid. Whereas if we only have non-partial functions, we know that if you give me an A, I'll give you a B, and this is my contract, and I will never fail to do that. And it gives you some sort of reproducibility and some sort of assurance that things will go the way you want. So how do we make use of programs? Well, the idea is to, of course, we have to do some of those nasty side effects, but the idea is to try to do them in a contained and least amount possible. So here I have this very abstract picture from the sky of our code where the green bit is the pure functional bit and the orange bit is the way you do the side effect. And we're trying to push all the side effect on the border of our code. So for instance, we could have most of our code written as pure functions, and we would have one file, one wrapper file, one bootstrapping file that connects the input, the database, the output, the logs, the screen, everything, and that basically connects our pure functions to that. But all of the side effect only really happens outside, and it really contained away. It's a bit like when we have unit test, when we abstract the dependencies. So this is not really a talk about pure functional programming, so I don't have a lot of time, but I just want to give you a quick list of benefits of pure functional programming. So it's easier to reason about abstract problems, local reasoning, facilitate testing. This is an interesting point. If you don't do any side effect, basically means that you are immutable. Of course, you can mutate variables within the scope of a function, but at the scope of the program, there is no state, so you can't mutate anything. So it's perfectly fine to have multiple threads reading variables at the same time. You only get race conditions when threads try to write on the same variables. So sometimes it makes parallelization easier due to lack of mutability. It can draw help from mathematical theories, and Monad is one of those examples, which we'll be doing today. At least for me, there is this strange satisfaction in building this highly composable code. And this is the last one, which really resonates with me, is that it's simpler when you're familiar. And I got this idea from, there is a virtual Java user group. If you haven't joined, I really recommend you join it. And they run those virtual conference when they have 24 hours, there's talk non-stop spanning different time zones. And last year, the keynote was done by Venkat, and he talked about the art of simplicity. And he said something which I found amazing. He put on the slide a Chinese character, and he asked the audience, do you think this is complicated? And I felt myself, well, I don't read and speak Chinese, so yes, to me it seems complicated. But actually, what the sign meant simple. And it basically, the lesson was that familiarity and simplicity are orthogonal principles, that you cannot often change the complexity of a problem. If you have a business case that is complex, you can't do anything about that. However, as human beings, we can learn, so we can change our familiarity with tools. And the key here with functional programming is that it might seem complex, but actually it's just because you're not familiar with it. And I will show you some example at the end how simple the functional code look compared to the non-functional code. And it's because once you've learned the vocabulary, once you've learned a few key principles, everything is simpler. So before we talk about Monad, we need to talk about another usual suspect called functor. So we'll talk about functor, we'll put functor on the side, and we will use functor at the end. So I promise everything connects in the end. This is part of the journey I was talking about. So functor. In the context of types, functors are polymorphic data constructors. So if you think about any generic that you can have in Java, a list of A, an optional of A being any type, those are functors. It's not a definition, but I'm giving you some examples. They're basically containers for types. So if you think about functor as a function, it's a function of type. It takes a type and returns a new type. So for instance, I could have the string type, and using the list functor, I get list of string, which is a new type. And if I have the integer type, I can get list of integer. So let's look at some example. So here now I'm going to start introducing those very abstract colors, which are types. So here, blue is just a type. It could be anything you can imagine. It could be a string, an integer, any of your own classes and objects, anything. So I start with this blue and I apply my functor f on it and I get another type, which is basically blue in a box. So here I have two types. And the new type is called the lifted type. This is only half the job of the functor. The other half is, what if I have another type, yellow? Well, I can also lift my type yellow. So here I have four types. I have blue, blue in the box, yellow, yellow in the box. Now, what if I had the function f that goes from blue to yellow? Well, the functor must provide a function, which is called the lifted function, that goes from blue in the box to yellow in the box. So here in this diagram, I have four types and two functions. And the function that lifts the function is called map. So map is a higher order function. It takes a function and returns a new function. So if we look at the types, I have f, which takes a type A and returns a new type called fa. I've got my small function from A to B. Now, map. We are familiar now with the carried notation. So it's a function that takes two arguments. First, a function from A to B, then the functor of A, and returns a new functor of B. So if I apply map on f, I just get a function from fa to fb. So now here it's kind of, I really want everyone to understand that these notations come from Haskell or other functional languages. In these languages, they do not have the concept of classes. Therefore, they cannot write method class. So you might be familiar, for instance, with map as being part of the optional or the list or the stream interface, pardon me. And they're not written like that. So the reason is because you could imagine this as a static method. It's a static method because it takes first the function, then it takes the functor in which you want to apply in the context of map, and then you get another one. But in Java, because this functor will be a class, like optional or list, I can write map inside that. So it means that I don't need this one. I just have a function that takes one argument, that just takes a function. So if I have a functor of A, I just need the function from A to B and it returns a new functor of B. So these two ways are completely equivalent. Either I write it as a static method, or I write it as a class method. So let's look at some examples. If I have a function f from blue to yellow, let's look at two examples of functors. The first one is optional. You might be familiar with optional, which was introduced in Java 8. The idea is that you want to model that a method can have two outcomes. If you say optional of blue, the function can return the blue, in which case we say it's a sum of blue, or it doesn't return, it's just empty. So to implement map f, here I need to I need to find what map f does for each of these two cases. And here, this is one of those very interesting cases in functional programming where there is only one possible implementation for this method. And the reason for that is because my type blue and yellows, they can be anything. I can make zero assumption for them. So, well, let's have a look. In the case where I have sum of blue, basically it means I have a blue and I have a function from blue to yellow. Well, the only thing I can do is apply my function on my blue, which I get a yellow. Now I know that I need to return an optional. Well, I just put my yellow in my optional and I return sum of yellow. Now in the case of the empty, I have nothing. What can I do? Nothing. I just return empty. And this is the only implementation that I would compile and that would actually make sense. Let's look at a list now. If I have a list of blues, with elements 1 and 2. So I have a bunch of blues and I have a function from blue to yellow. The only thing I can do is apply my function f on all of them and return a new list containing my new numbers. So here I had 1 blue, 2 blue, and I get a new list, which is 1 yellow, 2 yellow. And here, this is the only implementation. So something that is really important to understand with map is that map, it opens the box, give what's inside the box to the function, and then puts it back into a box and returns. So it means that map f does not change the structure of the functor of the type that we're looking at. It only changes the content. We see that in the case of optional, when we had a sum, we still have a sum. When we had an empty, we still have an empty. I have a list of 2 elements or n elements. I will have a list of 2 or n elements. The functor changes the content, not the structure. So this is the summary of the functor. The container for types. The map is a high order function that can lift functions. And lifted function changed the content of the box, not the box. And the structure is unchanged. So this is the first definition I want you to remember, that a functor is something that has map. So if we remember Boromir from the beginning, he's getting a bit upset here because this is not a mathematically sound definition. But I honestly really don't care for now. I really want you to remember that if you see something that has a map, then it is a functor. Okay, and if you remember that, you're 95% correct and you will spot a functor in 100% of the time. So now we can finally talk about monads. So you can put functor on the side of your head and we can finally look about monads. So I haven't mentioned Bartosz Chmielewski yet. He's basically a physicist, a mathematician, and he does a lot of work into explaining category theory to programmers. And as I mentioned very briefly what category theory was, it's this very abstract mathematical framework that supports and is the powerhouse of functional programming. And he has a blog post about monad, and he observed that so many people are scared of monad and they really don't understand them. And he has a theory behind that. And to prove the theory, he has this little game. That the game is you have to guess an object. And to guess this object, I'm going to give you a list of examples of how this object can be used. And you will have to guess what this object is. So let's look at an example. Well, this object can be used to fix the CO2 scrubbers on board of Apollo 13. So it must be something to do with space. Oh, it can treat water. So maybe it can treat water in space. Actually, it can fix an iPhone 4 drop code issue. It can make a prom dress and build a suspension bridge. So now we're kind of like really confused. I mean, what have all these use cases in common? So is there anyone in the audience that would guess what this object is? Yes, it's a duct tape. So maybe a few people would have guessed that, but I really don't think anyone would argue that this is a good way of explaining how duct tape works. If a child asks you what a duct tape, you would say, oh, it's something that can stick things. You would not go through this really random list of use cases. And this is what's happening with monad. If you read articles about monad, people will say, oh, you have the list monad, the state monad, the optional monad, the future monad, and that's it. And they will not tell you what monad is. They will just give you some examples. So the lesson to take from that is, if you want to understand what monad is, you should not look at examples. And because we are much smarter, we're going to look at the use case, which is completely different. So the use case is, I take a string, I receive a string as an input containing 2 numbers, and the program must return the division of the 2 numbers. So, we've been programming for some years now. We think we can tackle that. And we've heard about this new pure functional programming thing going on. So let's try that. So we're going to break down this problem into 3 functions. So what are the functions doing? Well, the first thing I need to do is I have a string. I'll have to split it. I'll split with the comma and I will get a pair of string. Then I should transform this pair of string into a pair of double, which is called parsing. And then eventually I will do the division. So let's write those functions in Java. So I'm lying a little bit. This code is almost Java. I'm pretending that we have pairs in Java. So when I write string, this is basically just 2 pairs. If I want it to be real Java, I would have to write it pair. I would have to import the pair from Apache Common or from Spring perhaps, and it wouldn't fit on the slide. So please just pretend that we have pairs. So very simple. My first function split takes a string, which is my input type, returns a pair of string. Then my function parse takes a pair of string, returns a pair of double, and eventually my function divide takes a pair of double and returns a double. Now the interesting thing is that something by design happens with the type. If I look at the split type, let's say it goes from blue to yellow, blue being string and yellow being pair of string, well, actually the parse function aligns. The end of the split is the beginning of parse. And I have the same with divide. The beginning of divide aligns with the beginning of parse. So basically, it means that we can write our program as a one-line function using function composition. We can say that it's divide after parse after split. So we split, we start, we divide. Now, of course, you might have noticed that this program is not perfect. The reason is because things can go wrong. We have our code is not safe, so that the split function, the split function can fail. Maybe there is no comma, but there's more than one comma. The parse function can fail. Maybe there is no number, and eventually the division can fail if we divide by 0. So now we have this exception. It means that our program is partial. If we think of our program as a function from string to double, for certain string, our program will fail, and this is not good. So what can we do? Well, there's not many things we can do. One of the things we can do is we can try to change the return type of every function to be an embellished type. So let me explain that. If I have a function from blue to yellow, I transform that function, I refactor my code to something from blue to something else, something of yellow, and I will call it a wrapper or embellished. It's another type that is generic in yellow, but is not yellow. How does it help? Well, you actually already know some of those types. The first example is optional. Instead of returning, let's say, a string, you can return an optional of string, and then you can choose to return optional of something or return empty. You've changed the return type. Another possible wrapper type that we don't have in Java natively is called the either type. So in the optional type, we only have a generic type for the result type, but not for the error. But actually with the either, we can use the left type to explain what went wrong. So this left type could be just a string, something happened, or it could be an exception. And if my program fails, I can return an left of exception, or I can return either of my result. And here, returning an exception is very different than throwing an exception. It doesn't interrupt the normal flow of the program. Another one you might be familiar with is asynchronous processes. So if I have a function that returns a string, I can change it to a function that returns a completable feature of a string. And now my function is enhanced. It can do something else. It can model the fact that it's asynchronous. It is returned something that will yield into a string. Logging is another case. So here I have this function called getMagicNumber. Instead of returning an integer, I return a pair. So here I use the real pair of integer and string. And as I run this code, I use the string builder to build the contribution of that method. And in the end, I return the magic number and also the string. And the caller of all my function will be responsible for collating all of these pieces of logs together. And here I have a purely deterministic logs with no race condition into writing into a file. And finally, the last examples which you might know is, imagine I have this build URL function, which will return a string, but it needs some configuration. So I can't just do that. So instead, I return a function from properties to string, and using a lambda, I use this properties object to build my URL and return it. So again, here, just by changing the return type, I can do something else. So the problem in our program was that it was failing. So we're going to use optional, which is one of those wrapper type that can be used to fix exception handling. So now the split function returns an optional of a pair of string. The parse function returns an optional of the double, and the divide function returns an optional of double. And again, we haven't changed the input type. We've just changed the output type. And here now it's so this is basically how, this is how it looks. This is a beautiful code. Look, amazing it is. So first, what do? We call split on the string. We get an optional of string. We check if string is present. If it's present, we do a get, we pass it to parse, I get an optional. If it's present, I do a get, I pass it to divide, I get an optional. I check if it's present, eventually I return a get. Otherwise, it's empty. And the beauty with this sort of code is that imagine I had 15 functions to call. I can continue doing this using this beautiful pattern 15 times, and it works perfectly. So for us, it's the victory. We have managed, our program is fully working. We have a non-partial function. We have our code is written as a function from string to double, and it's defined for every possible string. Certain strings will return optional empty, but still defined. Now, I don't know how many of you know any functional programmers. There's usually one in each family. It's a bit like the weird uncle or auntie. And if you don't know much about functional programmers, I will tell you something about them. They're extremely greedy. And here we are happy because we're honest Java programmers, but they are not happy. And why are they not happy? Let's try to understand them a little bit. Let's try to give them a bit of credit. Well, if we look at the types now, the output of split doesn't align with parse anymore. And the output of parse doesn't align with divide anymore. So now we're like, okay, but where is my one-liner? Functional programmers, they love this one-liner. So that's the problem. So if we're trying to summarize what the problem is, well, if we have a function f that takes a blue and returns a yellow, it returns a yellow inside this wrapper type. And I have another function which takes a yellow and returns an orange in a wrapper type, but the type don't match. How do we compose them? So to compose them, we want to define a new operator, which is called the Kleisli arrow, after Mr. Kleisli, who invented it. But because it looks like a fish, some people call it the fish operator. That is not my invention. This is the genuine nickname for this function. So what does it do? If we look at the type, if we have a function f that goes from a to n of b, and n being my wrapper type, and g from b to m of c, then g fish after will basically be able to go from a to mc to compose this function even though the type don't match. So this is a bit like the function composition operator, but on steroid. So this is the big question. How can we compose those wrapper types? So now we remember that we had a section on functor, because so far I had made no assumption on what those type was. So let's say we could have chosen a lot of type for our wrapper types. So now we will only choose those that are certified ISO functor, these are functor. It means that they have map. So if I have my function f now returns a yellow into a box, and my function g will take a yellow and return a orange into a box. Now, this is again one of the times in functional programming. I mean, what can I do? Now I took a blue, I applied f, now I have this, which is a functor. A functor has map. Remember, functor is map. So here I would need a function that to do map, I will have to apply map on a function that takes a yellow. Oh, here is a function that takes a yellow. And here is the part that might trip you a little bit, but actually it's actually quite straightforward. Remember that map, it opens the box, give what's inside the box to the function, and get the return of the function and put it back into the box. Well, let's just do that. Boom. Now I have a box in a box. And why I have a box in a box? Well, the outer box is because I'm in the context of a functor. And in a functor, I always keep the box. If I started with the box, I have a box. And the inside one was because this is what the function g gave me. So now I have a box in a box. I have a Tupperware in a Tupperware. And this is basically map g after f. And here, something I should have mentioned before, but all of these boxes, they're the same type, right? So you can't be mixing options. Let's say if we think about the option functor and the list functor, we can't mix them. It has to be here, for instance, they will all be optional. So if we look in types, I see that a map g after f, it goes from a to mmc. So I have functor and the functor. But what I really wanted for my fish operator, I wanted to go from a to m of c. So I'm almost there. What we really need now is to have something that can go from MMT to M. So basically something that can remove the unnecessary box, the unnecessary Tupperware in the middle. So let's assume now on top of, remember now, here we are trying to find out which of those wrapper types we could be using. So now we've said the first criteria is that they should be functor. So now let's apply a second criteria. Let's say that they have a flatten function. And the flatten function, it takes a type that is in two boxes and just remove the unnecessary box. So let's start from the beginning. I take my blue, I apply my F. I get yellow in the box. Then I apply map G, I get orange in two boxes. Then I apply flatten, and I get orange in the box. And there it is. If we do flatten after map G after F, we found the fish. This is exactly what we wanted. If we look at the types, we wanted exactly that. We wanted something that goes from A, which is blue, to M of C, which is box of orange. So the fish operator equals flatten after map after F. First F, then map G, then flatten. And this is what a monad is. A monad is a functor that has flatten operation. So here, Boromir is getting a little bit upset again because this is, again, not a mathematically sound definition. But for now, I think you can forget about this. Just remember that a monad is a functor that has flatten. But actually, if you wanted to forget that, you could, because there's another definition that is even easier than that. If we come back to what we had, one of the operation we did, which was first calling map, then calling flatten. We can call this flat map. So flat map G is first mapping G and then calling flatten. And if I look at the type, well, the fish operator is basically just calling flat map. So if we have this code here, I have all this space that the types do not match with each other, I can still chain everything. I can still do split and then pass and then divide and wrap them all into one function that pretends, basically this looks exactly like the first part when I could compose everything, even though the types don't match. So you might be a bit confused of what's the difference between the fish operator and flat map. Well, I want to give you an example. Think about the add function. It's a function that takes two int, remember the caret form, and returns another int. So when you write, usually in any language, when you write a plus b with the plus operator, the compiler rewrites that as a colon a and b. So basically, plus is like add. Plus is the infixed operator for add. And that's actually the same thing happening with flat map and fish operator. We actually can see that g fish operator f is equal to flat map gf. So actually, fish operator is like flat map, is the operator that corresponds to flat map. And this is the definition that you should remember. Monad is a type that has flat map. So again, this is not mathematically correct, but who cares? If you remember that monad is something that has flat map, you will always be able to, you basically know what monad is. And there is, this is not that complicated. So just to summarize again, a monad is a functor that has flatten or something that has flat map. And I didn't say that, but if you have flat map, you can implement flatten and map as well. Flatten is more powerful. So what are the advantages? Well, you can manage and control side effect. Remember, the whole reason we had those wrapper types is because we wanted to solve a problem of side effect. And here we had the problem with the side effect of exceptions, but actually, so we use optionals, but we could do the same thing with any other side effect, and there is always a monad corresponding to side effect. Now, we can program a side effect as if they're not here, and this is what I called the cherry on top of the cake. Basically, now, if we say that if you have some side effects, you can avoid doing them by choosing a wrapper type that is a monad. And if you do that, because of flat map, you can manage the side effect, but your code will still look as if you're not managing it. And it really is this cherry on top of the cake. So monad makes partial function total. So now, because we used an optional in our case, our program is defined on every single string. And we can compose function with side effect using flat map. I just want to remind you of the monads that you already know. You know about optional, maybe not either. You know about the computable future. So in Java, computable future does not have a method called flat map, but there's one method called and then. And if you look at the signature, if you have a computable future of type A, it's going to take a function from A to computable future of B. And this really is a flat map. It's a bit of a shame that it wasn't called flat map. And you can use monads for logging and environment, that sort of things. So remember, this is how the code, the non-functional code look when we use optional without knowing that optional was a monad. And look how it looks now. I really hope that your mind is blown right now. Look how much simpler it is. Let me take you through that code. So our program is a function from string to optional of double. I take a string I call split. Now this split returns me an optional. I know that optional is a monad, so I can use flat map. I use flat map on it. Now I pass a lambda. Inside my lambda, I have access to what's inside the split operation. So this is my split string. I pass it to pass, which returns an optional. Again, the whole thing is an optional. I can call flat map again. I have access to the pass string, the passed pair. I give it to divide and done. And the beauty of this code is that it's really efficient. If my split function, for instance, failed, it's going to skip the rest. Remember that flat map uses map, and that we looked at the beginning at optional. In the case when it's empty, it just is empty. It doesn't even call the rest. So if the code were to fail here, none of this would be actually called. I mean, none of the lambdas would actually be called. I'm not going to call path function. I'm not going to call divide. They get skipped completely. And if you open the optional class in Java, you will see that this is the case. Now you might be wondering, oh, when should I use map or when shall I not use flat map? So in the context of optional, if you have a function that you know cannot fail, so for instance, if you want to take a string and make it uppercase, for instance, you know this cannot really fail. So you can write a function that says to uppercase, or actually it's already written. So in this case, you can just do a map. You can just take your optional of string and you can map it. Now, if you want to have another operation that you know can fail, for instance, you want to apply some regex or you want to do some passing, then you create a function that returns an optional and you return empty if it fails. And instead of calling map, you call flat map. So the only difference is look at what your function returns. Now I want to show you something else. You know, I was talking about the imperative and declarative as type ways of programming languages, and actually people joke. So Haskell is considered the top, the king of functional languages. So it's the king of declarative languages, but actually people joke that Haskell is the best imperative language. And I'm going to show that to you, not in Haskell because it's a bit difficult if you're not familiar with it, but in Scala, which is very close to Java. So in Scala, we create function by calling the def, just means the function. We write the output type at the end, and the only difference is that optional is called option. So very simple split function, takes a string, returns an option of pair of string, and is the same for the rest. And look what we can do in Scala. We can use something called a for comprehension. And this is quite really interesting. I basically write for, and then I create a variable split. And instead of saying, so if I wrote split equals split, the type of my split variable would be the output of split, which is an option of string. But when I write with the arrow like that, because it's a monad, actually, look, I can pass split directly to my next phase. It's because the type of split is what's inside the monad, and it's the same for pass. Pass because what's inside the pass, so not without the optional. Divide without the optional. In the end, I just return divide. And basically what happens is behind the scene, the Scala compiler will rewrite this as a bunch of flat map, exactly the same way which we've seen before. And another beauty of this code is because Scala knows what a monad is. If you were to write your own data structure, for instance, you could write your own list or your own future, and they happen to be monads. And because they're monads, you could use them in Scala in this syntax. The syntax works for any monad, and I find this quite incredible. Something that I've said before, but I really want you to understand the context of monad. So this is a little diagram to show what we're trying to do. So on the horizontal axis, whether we are unmanaged side effect or managed side effect. And on the vertical axis, whether we are composable or uncomposable. And we started here. At the beginning, we remember we had a nicely composable code, but we had exceptions. It was non-managed side effect. So we used the wrapper type to cross the quadrant to go into a managed side effect without composability. And this is where we had the victory kid. We could stop here. There's really nothing that we have to do, that we have, this step is perfectly fine. But because we're greedy, like functional programmers, we wanted the cherry on top of the cake, and we wanted to use monad to be in the ideal state where we have managed side effect and at the same time we're composable. So what are the key takeaways of this talk? Functors are containers of 4 types. Remember, functor is something that is a type that has a map function. Embellished wrap types help to manage side effect. If you choose them to be monad, then it's perfect. Monad is something that has flat map. And monads allow composition of wrapper types. So remember here, if you want to use those wrapper types, choose those that are certified monad, and they will make your life easier. Now, before you go, I don't want you to misunderstand me. I am not saying that you should aim in Java to write 100% pure functional code. That is really not a pragmatic approach. It's really not feasible. So I'm just saying be pragmatic. Don't try to change the world in one day. Just keep an eye out. Now that you know that you have this monad out there and it's there in Java, you can use it in streams, You can use it in optional. You can use it in computable future. You can rewrite some of that code, but you don't have to go crazy. You don't have to get rid of logging or even exceptions. Sometimes the exceptions in Java, they can be good. So now, if someone wanted to go to this talk, but they missed it, and they're going to ask you, oh, so you went to this talk, so what the F is a monad? Just tell them, a monad is the cherry on top of the cake that is actually a fish. So some sources, if you're interested in the theory, go and check out Bartosz Milewski, lectures on YouTube and blog posts. If you want to learn about functional programming, there's the functional programming book, which it's not a book about Scala, but it's a book about pure functional programming in Scala. And I put the link for the Art of Simplicity by Venkat, and also a talk from Brian Goetz from the 2017 JVM Language Summit, where he introduced his thinking already of how can we have pattern matching in Java. And I think I put this talk here to show that functional programming is coming into Java. And I want to say thank you to Bartosz Milewski, who I don't know, but he's been putting all this content online. Thank you to Georgiana for helping me with the math. And thank you, Julien, who's been my mentor through this journey of functional programming. And if you have any question, I will be very happy to answer them. And you can find me on Twitter as well. Thank you very much.